All right, folks, welcome back. Have to get started because we have a lot to cover today. So first thing, it's almost the end of the semester. So that means hopefully you all have all made some awesome progress on the final projects. We're planning to have people present in class this Thursday. A brief overview of the final projects. It doesn't have to be finalized. You have about 12 more days between this Thursday's final presentation to the following Tuesday when your final reports are due, and then we'll grade all those and then send the grades into the register. So this Thursday will be the final project presentations. Let me also give you some overview of the instructions. All this was posted on Piazza, but the expectation is that you should write between 8 to 9 pages of content for your final report. 8 pages for 2 students groups and 9 pages for 3 to 4 students. And it should cover at this point really a summary of everything that you've done throughout the semester. So most importantly, abstract intro of motivating a problem and why it's important, related work, which should be categorized by different sets of methods, not by individual papers, and also highlighting how your work differs, rigorously motivated problem statement, formalizing the problem, and of course your proposed method, which should be about 2 pages, would be the bulk of the report. That could be proposed new benchmark, proposed new AI method, proposed new evaluation strategy, simulation environment, and the like. But that should be the most important part. There should be a very nice overview figure to explain at a high level everything that's going on. Experimental methodology, experimental setup, data sets, baselines, and of course, you should have rigorous results and discussions. Results for the baselines, results for your method. Ideally, it works better, but we're not going to be grading on how much better it is. If it's better, that's great. You still want to see analysis of why you think your method improves. If it's not as good as the baselines, also don't worry, but please include some analysis of why you think that is the case and some future directions you could do to improve that. And finally, conclusion and future directions. And for the report presentation, that would be on this Thursday. Time limit for each project will be 8 minutes, roughly 7 to 9 slides. You don't have to dive too much into the problem and the related work. It should really cover the key new method and the key new experiments that you have, the initial results, and also what you kind of plan to finish in the last 12 days before the report. Okay? So 8 minutes, 7 to 9 slides. Again, we'll have to extend class a little bit from 1 to 3 p.m. But again, let me know if there's any constraints. We'll try to schedule people to the appropriate time slots if you could send me the constraints by today. Great. Any questions on the final project logistics? No? Okay. And please, meet with myself and the TAs today after class. I think I'll be around from 2 all the way to 5, 6 p.m. if people want feedback and things to discuss before Thursday. Thursday, we'll also ask you some questions during the presentation and give you some feedback so you can have a solid final report by May 20th. All right. So to recap, we're almost at the end of the semester. This class has seen several modules. We started with basic foundations of AI research, data and common model architectures. We looked at multimodal AI, aligning different modalities, using them and transferring information from one to the other. We then had several lectures on basics of LLMs and large multimodal models. And Chanaka gave a guest lecture on generative AI. So today's diffusion models and flow matching models to generate more data. And this week and next week, the last 2 lectures will cover AI that's more interactive. So today we'll cover reinforcement learning, reasoning, and interactive AI. And next week we'll cover more human-AI interaction, some AI agents, and also how do you make sure these things are safe and ethical when deployed in the world. So today, basics of RL, and also so foundations of RL, and also modern reinforcement learning and how that's been used to align and make LLMs better at reasoning, and also in the final part, covering some applications in LLM agents. So firstly, RL basics. Again, the goal is not to really cover all the depth of RL, but only to the extent necessary to understand all of today's RL methods and how they're used for modern AI methods. So the biggest difference between RL and non-RL methods, supervised learning, is the fact that RL is dynamic, right? You have agents in some environment, and instead of just making one prediction, like classifying one image, you're usually trying to take a sequence of actions with the environment, which then gives them new states, new locations in the environment, in which case they might have to take more actions. And overall, this pattern continues, taking more actions, interacting with the environment, getting into new states. And the goal really is to maximize the agent's long-term reward in that environment. So to formalize this a little bit, usually people talk about RL in the context of MDPs, which are Markov decision processes. Essentially, it's a way of formalizing the fact that there's some set of states. This could be locations, if it's a robot navigating. Nowadays, people can also view states as, the words the language model has generated. So a state is some way of looking at, the data that you have currently in the world. There's a set of actions, which are actions, things that the model could do. If it's a robot, it could be, moving up, down, left, right. If it's a language model, it could be the output set of words that it could generate, and you'll get a set of actions. There's usually a transition function telling you from one state, if I take an action, what next states do I go to? And sometimes that's deterministic. If the robot moves right, it always ends up to the right. Sometimes it can also be some randomness in the environment. Very important is also the reward function. So if I'm in a particular state and I take some action, what reward do I get? And again, that could be, whether you've completed the task successfully. It could be a penalty on taking too much time or too much resources to complete the task. It could be how much the user is satisfied with the interaction. All are possible reward functions. And of course, there are other things like the state that you start in, a discount factor, which is actually quite important to make sure these RL methods converge. It's essentially telling you that a reward that you have right now is more valuable than rewards in the future. So you should try to maximize things that you can get. And horizon H is usually the total length of how many steps the agent interacts with the environment. And there's several key things you care about when this agent goes around different states and takes different actions and observes different rewards. First of all, is this idea of return, right? The idea that I don't want to just train an action to get the maximum reward at this immediate state. I want to be able to maximize a cumulative long-term addition of all the rewards that I get when interacting. So there will be reward at this immediate next time step, t+1 plus gamma of the reward at time t+2. Okay, that's the discount factor. Basically modeling that the immediate rewards might be, but money that you have right now is more valuable than rewards or money that you could get in the future. And you add up all the way towards the end of the interaction. So this is the key thing, right? Not just maximizing the immediate reward, but maximizing the addition of all rewards into the future. And of course, there's many cases in which the immediate reward isn't very good, but there's a much better reward in the future that you should try to optimize for. So that's the whole goal of RL, to maximize this long-term reward. And you're trying to maximize this long-term reward by learning a policy. The policy is a fancy way of saying whatever state I'm currently in, what is the distribution over actions I should take? So robot is here, it should move up or forward. If the language model has seen these words, it should output these other words. So a distribution over actions you should take given the current state. And I say again distribution because sometimes your policy is deterministic, so you always move forward at a particular state. Sometimes it can be also very helpful to have randomized policies. Like nowadays, these LLMs, they all have some temperature parameter. So there is some randomness in the next actions or next words that they generate. And as you mentioned, the goal is to really find the best policy, so the best distribution of next actions I should take from each state that maximizes the long-term cumulative reward. So the next reward that you get, but also all the rewards into the future. So conceptually, RL versus all previous supervised learning, there's several key differences. RL involves making a sequence of decisions, which can be arbitrarily long. And supervised learning looks at making just one step of decisions. In RL, you're trying to maximize the cumulative reward as a result of your sequence of decisions. And in supervised learning, you just maximize the immediate reward. In RL, sometimes you also have this issue of very sparse rewards. You might be interacting in a long sequence, and you only get a reward after 1,000 steps. After maybe a LM and a human converses for 1,000 words, do you only then get a reward? And that's what makes RL inherently challenging. But in supervised learning, you always get dense rewards. You know what the label is. Sometimes in RL, the environment may be unknown. There's always this issue of exploration. You're designing robots or your self-driving cars. You're not going to be able to map out every single road the self-driving car is going to go to or the robot is going to go to. there has to be some exploration of the environment, which again adds a layer of difficulty. And in supervised learning, typically, you know what are the possible things to predict, you know what are the possible inputs. I mean, that being said, there's one very trivial application of supervised learning methods to RL, and that's called imitation learning. So imagine as an example, you want to train a policy to navigate a self-driving car. So the states are whatever is on the windshield, what you see, and the actions are just how you should turn the steering wheel, for example. Double simplicity. Input states are what you see, and actions are turning the steering wheel. And of course, what you could do is you could get human experts to drive cars for a long time, and using that data, a sequence of states that a human saw, the actions that a human took, and the next state that a human saw, the next action that a human took. So you could get what we call expert trajectories, right? Someone who's expert driver performing this task. And then you could basically just do supervised learning by learning a function that takes in whatever states that were collected in this human expert data. That's your input S, and you just try to recreate what the human did by predicting the actions. So that can be a simple classification model. So that's called imitation learning. It's one example of reinforcement learning, but you can also see cases why it fails. Several big reasons. First of all, the biggest problem is distribution mismatch, right? If you see human expert drivers, they're of course going to drive well. They're going to turn and stop when they're supposed to stop and follow all the roads. And therefore, your model will only know when to take the right actions if they're on the correct path. But in the case that your model accidentally goes onto a wrong path, then it will not be able to recover, right? Because it has never seen examples of how human experts recover from accidentally not stopping at a stop sign or accidentally going off the road. So this distribution mismatch is going to be very difficult to tackle. If you start accidentally going into some suboptimal states, and it's also, again, going to be very difficult for the model to recover because in these expert demonstrations, you never see any suboptimal states. And of course, you also have logistical issues where sometimes expert trajectories are not always available. And even if they are always available, it requires lots of humans doing things, which can be very expensive. But sometimes if there is possibility of collecting human expert demonstrations, then imitation learning is a way of kind of initializing a good policy. But then you also have to tackle ways of letting the policy explore some suboptimal trajectories and also learning how to recover from those suboptimal trajectories. So diving deeper into RL, there's two general paradigms of RL. So one general paradigm is what is called model-based RL methods. In model-based methods, you often see these kind of like tree-like things that are drawn. So these trees essentially say, I'm going to start from a state, and maybe from this state, there's two possible actions. And given those two possible actions, there's two possibilities for the next states. And maybe each of them has, plus one reward for the top and minus one reward for the bottom. And then again, there's two more possible actions to take, which gives two more states. So this exponentially growing tree of nodes being the states, edges being the actions, and rewards that you observe when you go from one state to the next. So model-based RL at a high level is really just about constructing this tree and assigning the right values to the nodes in this tree that represent the long-term reward that you will get from each of these nodes. And in this case, in blue, I'm highlighting a policy. So this blue basically means if I'm in this state, here's the action I will take. If I'm in this state, here's the action I will take. So a policy is basically a traversal of this tree. So again, just quickly in just 5 minutes, there are several things that you need to learn if you're doing model-based RL. One is called a state value function. So given each of the states, what is the value of it? Where value means what is the expected long-term reward that I will get if I'm at that state. Again, long-term reward is the key, not just the immediate reward. So over here, you don't want to just say this state is -1. You want to assign a value to this state, accounting for the fact that you could get +100 in the future. And that's what we call state value functions. We usually annotate that as V of S. And again, there's two ways of writing it. One is the value of the state as you follow your current policy. So in this case, the value of this state S1 is that you follow the policy that you currently have from S1, you'll get -1, and you get +100, and so on. So the value is 99. Right? So it's accounted for not just the immediate -1, but also the fact that your policy will get you +100 in the future. So +99. Question?
Paul, you mentioned long-term reward, right?
Yes.
How is long-term reward defined in the science?
So just what I said, right? So if I'm looking at trying to find a value for this current state, I don't want to just say I'm going to get -1 if I take one action. I want to account for the fact that once I go here, there's going to be possibility of +100 in the future. So in this case, I'm not using any discount factor. So the total value is -1 +100 is 99.
So it doesn't matter the number of steps, but it needs to be positive 99. Is that what you're trying to say? It doesn't matter the number of steps the model is taking,
right?
But it needs to be some big number. I mean, it could be -10, -20, and then +150.
Sure. Yeah. Yes. So normally there'll be, there could be more things that I'm not drawing, and normally there might be a discount, so to show that things that are in the future may be less valuable. But in this case, if this blue thing is the policy, then it's going to get -1 now, you'll get +100 in the next step, and you get more. So yeah, we'll say that the total long-term value is 99.
Okay.
Are there decay functions that exist? Like I could imagine, for instance, let's say you're making an RL system for a doctor who's doing surgery, or there are many situations where you might not want, even if the outcome is better by waiting a long time or like doing a lot of computation,
right?
You might want to introduce a decay function to like reduce the amount of computation.
Yes, so that's exactly this discount factor.
Okay.
So that's why I write it as your total return is the reward at the immediate next time step plus gamma times the reward in the one step in the future, and then you kind of gamma squared times the future. And you can set that, usually gamma is something that's like less than 1, like 0.9 or something.
Oh, okay, cool.
So yes, sometimes a discount factor is actually very necessary to make sure some of these methods converge. Otherwise, you just keep going and it's a small reward, you'll keep trying to search for it. Great. Okay, so that's the value of the state following your policy. And another key definition is the optimal value of a state over all possible policies that you can take. And if you were to compute it for, again, this S1, you realize that, for example, this is already your optimal policy. So the answer for V star of S1 is also 99. Just a quickly, also a very subtle point. Sometimes people define not just the value of a state, but a value of a state action pair. So if I'm in a particular state and I take a particular action, then what is the long-term value of that state action? So again, some examples. And people label that as Q. So you'll see Q as A and you see V of S. So in this case, Q, following a policy pipe starting from S1 and going up, is that you see +1 and then you see +2, right? So that's +3. And so if you go from S1 and you go down, then you see this, you see 99. So that's basically a way of estimating values of states and also actions that you take from that state. And likewise, you can basically say what is the optimal state action function. So in this case, you look at this, your Q star. If you take S1 and you go up, you actually realize that this policy is suboptimal. Right? In fact, you should have gone here and gone there instead. So then that's why your best state value function over the best policy is 4 instead of 3. So a lot of model-based RL is exactly about deriving these QSA and V of S. Back in the days, people would use dynamic programming when exploring the tree. Nowadays, people, of course, use neural networks to approximate Q of SA and V of S. But once you derive it, the optimal policy can essentially be done by looking at it as a tree search problem. You're basically going to try to traverse your tree, and each time you're going to find the action that maximizes either your V of S or maximizes your QSA. So basically, your tree search problem. Also, another point is that these Qs and Vs are interchangeable. If you have one, you can also derive the other. Great. So that's briefly model-based RL. So People have seen, AlphaGo and some of the chess playing, game playing. They're mostly all model based. So they have states which are states of the game. There's possible actions that you can take, and your goal is really to estimate for each of the potential states of the pieces what is the long-term reward, right? So not just did I just take somebody's piece in the immediate step, but long-term, what's the likelihood I will win? So AlphaGo essentially just trains CNNs on these game boards by viewing them as images and training them in a way such that the CNN outputs V of S, the value of the state in the long term. And then once you have each of these V of S, you can essentially take argmax locally because your V of S already accounts for long-term reward. So now you can take your local argmax, which is just traversing your tree. So that's model-based RL. Another paradigm is policy-based RL. So in policy-based RL, we're not going to build a tree, and we're not going to worry about estimating values of each state and each action. In policy-based RL, all I'm going to do is just directly learn a policy. And I'm going to view that as essentially some function that takes in states and outputs actions. So in this case, this Pong game, your state is image of a game, and your action is whether I should move up or down. And most of modern, when you hear RL and LLMs, they all go with these policy-based methods. So we'll cover policy-based methods in primarily detail in the lecture. But before covering policy-based methods, I want to highlight, again, this is a big debate, whether model-based methods are better or whether policy-based methods are better. And here I've listed a long set of pros and cons for each approach. So in model-based RL, you're actually learning a model of the environment. You're learning this tree and each possible state action transition. In policy-based RL, you only learn the policy, but you don't care about learning a model of the environment. And as a result, because model-based RLs learn a model, they are much better for planning. So you can simulate other potential actions by traversing this tree. They're much more sample efficient, but they come at a cost of being more complex. On the other hand, policy-based methods, they don't allow you to do planning. They don't allow you to, they have much higher sample efficiency, but the training algorithms are typically much easier to implement. And there's a lot more, strengths and weaknesses. This also covers some famous algorithms for model-based RL, and this covers some famous algorithms for policy-based RL. All right. So policy-based RL. So again, I'm going to use this motivating example. This is like a game of Pong. So you're going to control one of these paddles against your opponent, and your two options is to move up or down to bounce the ping pong ball back towards your opponent's side. You win a point if you manage to get it across. You lose a point if you manage to you let the ball in on your own side. So now the goal is to just train a model that takes in this state, which is the screenshot of the game, and output just two things, whether you should move up or down. Right? So it's a binary classification problem. And your goal is to essentially train this model. So how do we train this model? So first, suppose you have labels. So if, let's say somebody, for example, follow human experts, and these human experts showed you at every state what the human did. Did they move up or down? So this is expert labels, expert trajectories. And then what you would do is you would typically just class this as a supervised learning problem, right? S comes in, and your labels either up or down, and you maximize your log probabilities. So log probability of moving up when you actually moved up, and maximize log probability of moving down when the label was down. So that's basically your cross entropy loss. That's what you would do if there was labels. But of course, you don't have labels, or labels are expensive. So what policy-based methods would do is that you would first have a policy. So a policy is just a way of saying, I have some states and I take some actions. And I'm going to just try this policy out. So maybe in the first run, your policy said up, up, down, down. And your second run, you had sampled something else. And your third run, you again sample something else. So these are just ways of your model acting based on your current policy. And let's say you run this in your game, and you realize that in your first sequence of actions, so your first sample from your policy, you won. So you're very lucky that you won. And then in your second and third runs, you weren't lucky and you lost. Okay, so you can basically observe whether you won or lost by whether a point went to you or the point went against you. So what you would then do is that you will basically treat the sequences in which you won. I know it was by luck probably you won, but treat that as good examples. So I would want to maximize each of the actions in the sequence that led to you winning. And you will also treat the sequence of actions that led to you losing. You were unlucky and therefore as bad examples. So I'm going to penalize each of the actions in the sequences that led to you losing. So what does that look like? Basically maximize log probabilities of each of the actions when you won, and maximize -1 times each of the log probabilities of the 4 actions in which you lost. So in general, you can think about it as a general objective function that maximizes sum over each of the actions, the reward, Ri, whether that is +1 or -1 in this case, and the log probabilities of each of the actions in that sequence. So in fact, that explains policy-based RO. It's as simple as that. This very first algorithm that came out back in the days was called reinforced algorithm. You would basically start with some policy, pi of a given s, assume it's differentiable, so it can be a neural network. You would initialize the parameters randomly, and you just loop forever. Use that policy to generate an episode. So take actions from your states. So in Pong, it was moving up and down. That was one episode, and you saw some rewards. And you move it up and down again. You saw some other rewards, and so on. Following a policy. And then for each step of the episode, I'm just going to maximize this function. So again, this function was just G is your reward in that sequence. So add up each of the rewards as given by this equation. And then this is your gradient of your log probabilities of the action given those sequences. So exactly this equation, except now your reward is just added over each of the steps. And you also realize that that this gamma here is a discounting factor that you mentioned. So you should kind of penalize good rewards in the future and prefer to have them now. But that's all policy gradient is. So sampling different actions from your policy, seeing what the rewards are, and either pushing up or pushing down the actions based on whether rewards are positive or negative. This point over here, following a policy, I should also note that epsilon greedy is something that is super important. So what does epsilon greedy mean? Basically, when you initialize your policy is going to be very bad, right? It's basically going to give you random actions. So that means you shouldn't always follow your policy to take actions. And instead, you should sometimes just take random actions. So we call that exploration. Take random actions regardless of your policy. So usually with epsilon probability, you will just take some random action. And then as you slowly start training your model, you push up the probabilities of good actions and you push down the probabilities of bad actions. Now your policy gets better, right? So once your policy gets better, you will slowly start to prefer sampling from your policy and not sample too much from random policies. So basically this epsilon will start out really high and your epsilon will slowly get smaller. So we call that the exploration, so sampling random things, and exploitation, so following what your policy tells you. Okay, so that's basically policy gradients. Again, maximizing reward scaled by the log probabilities. The log probability scaled by the rewards. So your reward is positive, increase the probabilities of the actions. Reward is negative, decrease the probabilities of your actions. This is the vanilla policy gradients. There's been a lot of improvements over the years because this has several issues. One is that it has very high variance. Why is it I say very high variance is that usually the raw reward itself might not be very meaningful, right? Sometimes I have games where you always get positive reward. You just want to get more positive and less positive. Sometimes you have games that are always negative reward and you just want to stay closer to 0. So sometimes the raw reward is not very meaningful. And what is important then is how the reward changes over time as compared to the rolling average of the rewards. So a big, big innovation or a big trick to improve performance is to compare the rewards to a baseline and use the relative improvement. So now that's a new function. Biggest difference is that this reward of your trajectory, your sequence of action, you subtract the baseline. And baseline can be something like exponential moving average of the rewards. Okay, so subtracting baseline substantially improves the stability of policy-based methods. Now, of course, people have also explored much better baselines, and therefore this actor-critic method was developed. A better baseline basically combines your policy-based methods with your model-based methods. Recall that we defined Q and V, right? So V was V of S. So how good a state is as measured by the long-term rewards from that state. And Q was QSA. So how good the state and action pair is by looking at the long-term rewards from that state and action. So in fact, the difference between QSA and V of S, we usually call that A of SA, where A stands for the advantage function. An advantage basically means what is the advantage of taking a particular action from that state. And again, this advantage is measured in terms of not just the immediate reward, but in terms of the long-term expected rewards. So if this AFSA is very big, that means we are very happy with this action because it gives us much better long-term reward. If A of SA is small or negative, we're very unhappy with the action because it gives us negative long-term reward. So that gives you this new estimator by essentially, again, maximizing log probabilities of the actions in your sequence, but now scaled by this advantage function. So how much better Q of SA is as compared to the baseline V of S. So we call those actor-critic methods. This was, extremely popular. I think kickstarted a lot of deep reinforcement learning research, 2016 to 2020. And in this case, you have to learn two models because, as you mentioned here, first you need a model to learn a policy. So what actions I should take from a sequence. But I also need models to learn these Q and V functions. Like this was the model-based RL and the tree that I was showing. So these actor-critic models exactly maintain two models. One is the actor model. The actor model learns a policy. So state comes in. The actor learns a distribution of actions over a given your state. So that's your policy or your actor. And at the same time, the other model is what we call a critic. So the critic essentially learns, in this case, Q of SA. It learns to criticize and evaluate the value of state and actions that the model sees. So and these two functions are basically trained together using different objectives. The critic evaluates how good a baseline action is. I'm not going to cover too much of this. If people have seen Q-learning before or DQN before, that's basically how these model-based methods were, approximated with deep learning. And the actor, which decides what the policy is again your policy gradient function. So your log probabilities scaled by your advantage function. And that's your advantage function. All right. I know this might be more content than usual lectures, but any questions so far? Okay. So almost there at the exciting parts, which is about how these RL methods have intersected with LLMs. But before that, several other small improvements. One of them is called proximal policy optimization. So everything before was kind of policy gradients, policy optimization, and this new method called proximal policy optimization. And there were several new methods within this space. One of them is called trust region policy optimization. And the biggest difference is that you are still going to do policy gradients. You're still going to maximize the log probabilities. But now the biggest difference is that you are trying to make sure that your policy doesn't change too much over time. And measuring that you shouldn't change too much by limiting a KL divergence between the new policy after the gradient update and the old policy before the gradient update. So if there's a current point, you want to make sure your proposed point is very close inside. And similarly, this visually, this was your actions and your policy. You don't want it to go too different from what it previously was. So that's trust region policy optimization 2015. And then proximal policy optimization was a further approximation of that by saying you don't actually need to formally measure the KL divergence between your two policy distributions, old and new, but now I'm just going to clip the gradient. So whatever the policy gradient was, the log probabilities just clip it within a certain range. So this is the equation if you're inclined. This is the ratio between your new policy, pi of a and s, and the old policy, pi old a given s. And you're going to kind of clip this region between 1 minus epsilon and 1 plus epsilon. So clip that ratio. So you're within kind of an epsilon ball each time you update your model. And PPO essentially is the RL method that people use in RL for human feedback, right? That is kind of used to align these LLMs today. And briefly, how these methods work is that in step 0, you will first pre-train your LLM, and then you will do supervised fine-tuning on your LLM. So what I've done pre-training is just taking all your internet text, predicting one word after the other, and supervised fine-tuning, sometimes we also call it instruction tuning, collects human written demonstrations of questions and answers, and does next token prediction on those questions and answers. So you'll have seen this. And then in step 1, now this is when the kind of the RL-based alignment comes in. So for each prompt, you're going to treat LLM as the policy. So policy as outputting actions given states. It's just that now it's outputting sequences of words given states, which are your prompts and the previous words that you've generated. So you can view LLM as a policy, and you will sample multiple responses from the model. So this could be one response, another response, another response. Same as what we saw for the ping pong game. And in step 2, you had humans rank these outputs by quality. So that was where the human feedback came in. But of course, you cannot rely always on humans labeling the responses, right? That will not generalize outside of the lab. So now you would then train a reward model, which basically predicts and tries to mimic human preferences. So now you can label any other response that, even though was not labeled by a human, could be labeled by the reward model. So you get some rewards. Same thing again as the ping pong game. It's just now it's a bit more complex than just +1 and -1. One subtle thing is that these reward models predict human preferences given full model responses, given full completions of the dialogue with a human. And then in step 4, you're using RL, and we started with PPO. The first algorithm they used was exactly PPO, this proximal policy optimization, to fine-tune these LLMs to maximize these rewards. And again, maximizing this reward basically means taking the reward, multiplying by the log probabilities of the actions in that sequence. So a bit more detail, first human ranking and reward model. So that would be your prompts come in, you have a language model that generates some text, and humans will score each of the sentences whether they liked it or not. And then once these humans scored it, you would train on the inputs and what humans scored as a reward, and you train that using supervised learning to get a reward model. So you recover what the human rewards were given ground truth human labels. And of course, David mentioned this in LLMs. It's harder to assign objective rewards like 8 or 1.2 to just a dialogue. It's usually easier to compare one versus the other, like that humans prefer this over this. And therefore, you'll see some of these papers, they often have this kind of thing, which is basically a way of measuring the likelihood that one output was preferred over the other as a function of the actual rewards for each of the two sites. So basically a way of relating comparative rewards with absolute rewards. But yes, all of this is just ways of getting humans to rank and learning a reward model. And then in PPO, what happens is that, so what do you have so far? You have your actor model, which is your policy. There's your large language model. States are the prompt and what the model has generated so far. Actions are next words that it will generate. It will have this reward model that we just saw. So that has been already trained and frozen from humans rating these responses. And now it will just recreate and repredict these human preferences as a scalar reward. Again, these are on top of your full model responses, sort of full dialogue. And a third component is this value model. So this value model is the same as the critic model that we saw. So this is also going to be trained. It's going to be a critic model that essentially takes in, that estimates V of S, the value of states. So states in this case are just model responses, both partial and full model responses, sequence of words, and you predict a scalar reward. So this is exactly the same as your actor critic model, right? There is some actor model that is generating actions, in this case words, and there is a critic model that is assessing the values of words that you generate from each state. So how do you then apply RL to this setting? So you will start by, well, first generating responses. The LLM will produce multiple responses for each prompt. You will run your reward model to assign rewards to each of the output responses. And you will compute your advantage. Exactly like in actor critic, you will compute your advantage function. Over here, your policy is a language model given a prompt, and the policy, you generate some outputs. The outputs will be going to the reward model to get your R, and it also give you your value model, which gets kind of the baseline. Right? This advantage is basically how much your reward is better than the baseline that you would expect. So that's exactly the advantage function. And you want to interpret that as, how would generating a specific word outperform just, the average word that you would generate given that state and previous words. So this gives you your A function, and this A function would be the term that you use in your policy gradients to update your policy model, which is your LLM. And another subtle thing is that you would also, after optimizing your policy, you also update your value function. So you would try to train a better value model, and you want to think of this value model as, again, assessing goodness of an average word. So it seems complicated, right? Seems pretty complicated. And that was perhaps the biggest advantage of GRPO. It simplifies this by a lot. So you see previously you had policy model, you had reference model, reward model. And again, blue is frozen. I forgot to mention, blue is frozen, yellow is trained. So it had policy model, which is LLM. It had your value model, which estimates the average, how good the average word was. You had the reward model, which was how good this new word is. And you will compare the reward new word with the average value of a word. And you have a reference model. So that's LLM at the previous step. And it would have this KL penalty to make sure it didn't change too much, right? Remember, in proximal policy optimization, your KL has to make sure your policy doesn't change too much. So it's very complicated. And then GRPO came by and said a couple of things. Well, first, we're going to remove the value model. We're not going to have a value model that tracks the goodness of an average word. And we're not going to try to learn that. And instead, I'm just going to sample from my policy a group of responses. Each of them I score reward, and my advantage is basically just estimated by how good this reward was compared to the other rewards in the group. Okay, so you don't need a value model to as a baseline to measure the average goodness of a word. If you sample enough groups of responses, then just the rewards within those groups already allows you to compute what the average was, and therefore how much your reward was better than that average. So yes, getting rid of that value model, something that you don't have to train, you can get rid of it, makes things and makes life a lot easier. And you can see here, this is basically how your very simple. That's the big thing, is just the PPO objective with your KL. But a simple thing here is just this advantage function. The advantage is just the reward minus the mean of the G rewards in the group divided by the standard deviation of the G rewards in the group. So yes, key differences. Group of responses used to compute the advantage and the gradient updates. You are getting rid of the learned value function and just making it much simpler as a statistic of the rewards over a group without learning it, just basic statistics. And and then some further innovations came by where they even abandoned the reward model. So you don't have to train a complex reward model, copying human preferences, and just use some simple rule-based verifiers, like binary checks if your code runs, or how many test cases does your code pass, or how long your response was, or whether your response followed a certain format. So as you can see, a lot of innovations are as a result of simplification, and rather than much more complicated or advanced algorithms. Great. And here was just some I was looking at several blog posts, and I think a lot of people a lot of RL people. So right now, a lot of people who used to do RL for robotics and deep RL are now all investigating RL for LLMs. And a lot of people in RL community are thinking, GRPO simplified PPO so much, and it's surprising that people have never tried this. So this is a tweet that somebody said. The reason why no one has tried GRPO before is, well, we have. In reinforce, and remember reinforce was the very first algorithm we talked about, right? In reinforce, you update the policy by subtracting the baseline, which is typically the average reward from several trajectories, right? Your exponential moving average of the reward that you've seen so far. And this helps to reduce variability. In fact, theory shows that the ideal baseline is a total expected future reward from a state, often called the value. So your V of S, total expected reward from a state. And using a value function as the baseline is known as actor-critic approach. So you have the actor, which learns the policy, and the critic, which learns V of S and uses that as the baseline. And PPO is a stable version of that. Now, in traditional reinforced, the baseline can be any function of the current state. And traditionally, it's just the reward of the trajectories, the average of that in a single batch. And of course, in GRPO, this baseline is computed over 1,000 samples generated for each prompt, which is novel. So very much going, even before active critic, before the learned value function, to just a simple rolling average statistic of rewards for multiple prompts that you sampled. Great. Well, last two things. DPO is also something that people might have seen. Again, a variant on PPO, which is your policy optimization. So this box here is PPO, right? Remember, you had preference data, you had prompts X, and you had rankings, whether human thought one thing was better than the other. You would train a reward model to reflect your human ratings. And then once you had a reward model, you would use that using your policy gradient to obtain and update your policy model, right? So that's PPO. DPO is this line over here, which basically starts again with the same preference data, skips training the reward model, and skips PPO, but literally just does kind of training on the preference data using supervised learning, like supervised prediction on top of the preference data. Well, probably it's not right to say that it was supervised. They're kind of doing reinforcement learning on top of this preference data. I won't get into too much details, but there are some key differences. So DPO is much more efficient in terms of compute because it doesn't have to train a separate reward model and do RL using the reward model. So it's much more efficient in terms of compute, speed, and less engineering. It doesn't have to train a reward model. And doing training also doesn't have to decode online responses, which is usually what is slow. And PPO instead has to train on online data. So it's always training on the responses that you just collected. And while DPO trains on this pre-generated offline data. So point being, this is still kind of argument between the communities. PPO can be seen as online reinforcement learning, and DPO can be seen as offline reinforcement learning. And there's kind of two differences in what's happening. I think a simple analogy to look at it is that, let's say you want to train a policy on a self-driving car. Okay, so you're going to deploy it on your car, and as you drive your car, you're going to collect more data, you're going to see the rewards of how good you're driving, and you kind of update your model based on what you're actually experiencing online in the world. So that's online RL. And offline RL is more about, you've seen kind of videos of other people driving cars in different scenarios, not the one that you're actually driving in your life, but trying to learn from offline data. And people kind of argue between whether online is better or offline is better. But the biggest difference between PPO and DPO is that one is doing online RL and one is doing offline RL. But a big appeal again of DPO is that it's much more simple and it skips a lot of additional steps that were previously needed. All right, we're almost out of time. So let me wrap up. Several tips and training tricks for reinforcement learning. Oftentimes, it is always good to sanity check with fixed policies. So randomly initialized policies or policies that you have initialized from human expert demonstrations. because one of the biggest challenges in our realm is the fact that you are learning policies while the rewards themselves and the environments themselves are also changing. Usually it's good to monitor KL divergence, especially in algorithms where you're trying to enforce that your KL doesn't change too much, and your policy doesn't change too much. So making sure that is smooth. Plotting entropy over time. Entropy is just how high variance your actions are. So you want your actions to start off as high variance because you want to explore, and eventually you want your actions to be much more close to just taking one action. So the exploration at the beginning, but exploiting good actions afterwards. Use greedy rollouts for evaluation. Debug value functions separately. So usually in actor critic-like approaches, it's difficult because you're training two models. Your actor is your policy, and your critic learns the value. And you're training them kind of in opposition with each other. So just like GANs were hard to train, these actor critic models are also quite hard to train. So sometimes it's useful to kind of train one and freeze the other, and vice versa. Nowadays, gradient norm clipping is also crucial. Check advantage distribution. So if your advantage functions are learned well, they should almost always be like mean 0 and variance 1, right? Because you're essentially subtracting a baseline, the mean, the rolling mean, and dividing by the variance. So it should always follow a nice Gaussian distribution. That helps training. Train on frozen replay buffer. Use curriculum learning, and watch for mode collapse. Chanaka wrote these 10 things. Great. Okay, that's all for the lecture. So please, come by and chat with myself and the TAs later after class. Let us know how the final projects are going. We'll see everybody in class this Thursday for the presentations, and we'll put up the schedule tonight. Thanks, everyone.
Interested, why don't we have what are the limitations of going to online learning? Let's say platforms like ChatGPT, why don't we just do reinforcement learning